Hello and welcome back to my YouTube channel. My name is Professor Kavala, and today I'm going to be talking to you about the summing amplifier. And essentially what we're tasked to do here is solve for this V out of T. And what we're going to do first is define what the summing amplifier is. So the definition of the summing amplifier says that a summing amplifier is an op-amp circuit that combines several inputs and produces an output that is the weighted sum of the inputs. And essentially some quick examples, which I'm not going to go into too much detail on, are things like an audio mixer. And essentially, if you can imagine, if you have vocals plus a drum plus the guitar, you can use a summing amplifier to add all these signals up and control their amplification using their input resistances, as we will see towards the end of the video. Another use case is the DC offset. And essentially, this means similar to, let's say, you have an AC source at 0 volts and you have a DC source at 5 volts. You can add these two up and we will essentially get an AC source at 5 volts. And the last use case that I'll talk about is what's called a digital to analog converter. And essentially, this is a case where you have a digital signal and you want to convert it into an analog signal. Again, these are just high-level examples of where you can use a summing amplifier in. But now let's go ahead and solve for the voltage output of this amplifier. So before we dive in, we want to consider that this is what's called an ideal op amp. And in an ideal op amp, we say then that IN is equals to IP, which is very close to 0, where again, this here is the current IN into my negative terminal, and this here is the current IP into my positive terminal. Also, for an ideal op amp, when the negative terminal or the inverting terminal is connected to my feedback resistor, I say then that VN is the same as VP. So essentially, this voltage here, VP, will be the same as this voltage here, VN, or V negative. So what we can do now is we can write what we consider KCL equations at node Vn. And essentially this becomes I1, so this current here, plus I2, or this current here, plus I3, or this current here, has to equate to this I4, which is the current through the feedback resistor. And the reason why they all have to equal to I4 is because the current IN is equated to 0, so no current goes into my negative terminal of my op amp. So now what we can do here is we can solve for I1 by saying then that V1 minus Vn over R1 plus I2 is V2 minus Vn over R2 plus I3 is going to be V3 minus Vn over R3. And this is equated to I4, which is going to be Vn minus Vout over Rf. I hope this equation here, let me call this equation 1, makes sense. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. What I can then say is that Vn is equals to Vp, and Vp is equals to 0. So then this goes to 0, this is 0, this is 0, and this here is 0. So now what I'm going to do is I'm going to multiply the entire thing by minus Rf. And so what I get from my final equation is that Vout is equated to minus Rf over R1 times V1 plus minus Rf over R2 times V2 plus minus Rf over R3 times V3. And essentially this here is my final equation. And this is also referred to as what's called the summer. And essentially, the summer is considered that because the output is the weighted sum. So this is the weighted sum of my inputs. So I hope that makes sense. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. If you like the video, please give it a thumbs up, and please share the video to your colleagues. And if you like what the YouTube channel is providing, please consider subscribing to the channel. It really helps the algorithm. Thank you.